Okay, so it is time. So welcome everybody. And as always, the scenery that you might have discovered if the session had been live, please turn off your mics and webcam. And then just as a little reminder, so all the presentations are available on YouTube, the YouTube channel that we created for that. I noticed that many of you have already checked it, and do so. We put the videos of the presentations on, I would say, almost in real time. And so what I'm going to do right now, without further ado, is to give Jean-Marc Triscone, who will be the moderator of the session. I'm just going to appoint him co-host, and then he will do the all the necessary. Okay, there you go. So now, Jean-Marc, you have infinite power.
Okay, thank you very much, Mark. It is my pleasure as a co-organizer of the school to chair this morning session. We have today the pleasure to have for this seminar Dr. Jennifer Fowlie with us. A few words on Jennifer. She studied physics at the University of St. Andrews in Scotland. She then moved to Geneva, where she got her PhD in 2018. And for her PhD, she got the Springer Prize for the best thesis in Geneva for the year 2018. She's now a senior research and teaching assistant in Geneva. She's a specialist of complex oxides, oxide heterostructures, and oxide interface physics. She has been working a lot on Nickelates, a fascinating family of compounds, and it will be the subject of her seminar. I think you're now familiar with the system. If you have questions, just ask them through the chat. And at the end of the talk, I will give you the word. So with this, I think we can start. Jennifer, the floor is yours and you can share your screen. Jennifer, please.
Thank you. So everyone can see, everyone can hear?
Yeah.
Good. Okay, so it's really a pleasure to be here to present to you a research seminar for this school. I went to not this school, but similar ones when I was beginning my PhD, and it was really a very special few weeks. So I hope that you're enjoying this time, even though you're not leaving your home. So the subject of my seminar is going to be perovskite nickelates and heterostructuring. This is a very broad title, and in the end it would of course cover very many different studies, all of which are interesting in their own right. What I have done is just picked a few lines of research to explain in a bit more detail, not necessarily my own research either. I have tried to be kind of diplomatic in that sense. And importantly, I think what I want to do first is to explain the fundamental concepts which more or less correspond to the individual words in this title, perovskites, nickelates, and heterostructures. And I believe and I hope that the, let's say, the basics that I'm going to introduce will be useful to you as you go forward in your career, even if you don't work with perovskite, nickelates, or heterostructures. Okay, so the outline is a bit like this. The first half of the presentation is really going to be introducing concepts. So I'm going to explain the perovskite structure and different ways that we can describe it. Then why transition metal oxides are important. Then specifically introduce the nickelates, which are a family of transition metal oxide perovskites. And then I will go on to explain heterostructuring. And then the second half of the talk is going to be more specific, first on heterostructuring effect on nickelates, and then with a very specific goal in mind, which was the search for superconductivity in nickelates, I will explain 3 different approaches with varying levels of success, as you will see. So let's begin. The perovskite structure is like this. It's a very flexible structure, meaning that the different atomic sites can have very many different types of elements substituted onto them. You have the A site, which is the largest cation, which can be an alkali metal, alkali earth metal, or a rare earth, and of course in the rare earth nickelates, that's what it is. In the center of this octahedron, you have the B site. So this is the transition metal in transition metal oxides, or a post-transition metal sometimes. This is the cation that really determines the physics of the system. The A site cation plays a largely structural role. So normally when you refer to a family of perovskites, you just use the name of the one in the center of this octahedron. Now, this octahedron itself is important. So this is 6 oxygens that sit around the B site cation. And in 3 dimensions, this octahedron will be connected to another one right beside it, above it, below it, and in front and behind it. So it's a corner connected network of oxygen octahedra. So when you substitute different A and B site cations onto this type of perovskite unit cell, what you get is different distortions. So this means that what is shown here is what we call the pseudo-cubic unit cell, where you just simply think of the repeating unit of the structure as being a cube going between the centers of these A sites. But most of the perovskites are not that simple. Their primitive unit cell is bigger, and this is happening because of different types of distortions, which can be summarized like this. Cation displacements, so either the A or the B site, can be moved from the cubic sublattice, let's say. You can also have distortions of the shape of the octahedron, so this could be stretching or compressing of the octahedron, like you get in Young-Teller type distortion. And finally, and the one that I think I will go into the most detail on, you can have distortions of the overall octahedral network. So it means that the octahedra do not change their shape, but they change how they are connected to each other. Namely, they rotate and tilt with respect to each other. So this is now just 2 examples of the types of primitive unit cells that you can get when you do these types of distortions. So this is a rhombohedral unit cell, this is an orthorhombic unit cell. They are both very common in perovskites, and there are subtle differences between them. Basically, you obtain these unit cells from the cubic unit cell by just rotating the oxygen octahedron. Now, there exists a very useful way of explaining how the octahedra are rotated, and this is called Glaser notation. So that is what I have written at the bottom here. So I will explain on the next slide how Glaser notation works. But basically it tells you how the octahedra are rotating, and that's the only difference between these 2 unit cells. So how do you get these different unit cells? Well, you just change the different cations and the structure changes as a result. So Glaser notation. You have to visualize just an octahedron. Now I don't show the oxygens on the corners, but in principle they are there. And you allow this octahedron to rotate without changing its shape. So the bonds are somehow rigid. And then you look at the 3 crystallographic axes, A, B, C, and each one of these axes will receive a label, which will go here, here, and here. So A, B, and C. So which label lands first, second, or third tells you A, B, or C. And then if you have a repeated letter, so for example, AA, what it means is that the magnitude of the octahedral rotation around the A axis is equivalent to the one around the B axis. And then you get some superscripts on top. So if the superscript is a plus, this means you have an in-phase rotation along that axis. So along the A axis, all of the octahedra rotate in the same direction. Similarly, if you have a minus in the superscript, it means that all the octahedra rotate out of phase, so they're alternating one way and the other. So in this case, you have in-phase rotations and out-of-phase rotations, but they have the same magnitude in this example. And if you have a 0 in the superscript, it's a bit redundant, but it just means that there is no rotation or tilt around that axis. And what you do is you use the Greek letters alpha, beta, gamma to quantify the tilt. So you would say, in this case, for example, gamma is 0 degrees. So as an example, I just put perovskite. So this means the perovskite. This is the mineral perovskite that you can go and mine if you want to in Siberia. Annoyingly, the mineral perovskite is not a perfect perovskite. It's not an archetypal one. It has distortions of this type where you have equivalent magnitude rotations that are out of phase around the A and C axes. And in the B axis, you have in-phase rotations. Now, the archetypal perovskite, which is not perovskite, but it's perovskite-like, of course, is strontium titanate. At room temperature, it has no rotations around any of its axes, so you can just call it A0, 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 alpha equals beta equals gamma equals 0 degrees. Now, on the left here, I have a movie. I'm warning you that it's a movie because you need to be looking at this panel when it starts because it's kind of subtle. What it's going to do is it's going to go from the cubic perovskite like strontium titanate and become the distorted perovskite calcium titanate just by rotating these octahedra, and you will see that they are still able to keep their corners connected while doing this. So what you will see is a out of phase rotation around one axis, an out of phase rotation around the other axis, and finally an in phase rotation around the last axis. So when I say go, it will go. Okay, it's going now. Okay, that's an out of phase rotation, an out of phase rotation, and an in phase rotation. I hope that the frame rate of the video was clear enough for you to see that. But yeah, this is the kind of structure that you end up with. It's nice and distorted, and now the unit cell is much bigger. So that's Glaser notation. It was introduced in the 70s, and it's still used today. You will probably see it from time to time in papers, and it's probably very useful to be able to read and understand what is being explained by this very compact notation. So another way of describing distortions in the perovskites is through the Goldschmidt tolerance factor. So this is an empirical relationship between the sizes of the ionic radii. So this is the tolerance factor T, and it depends upon the ionic radius of the A site cation and the B site cation and the oxygen anion. And when you calculate this, it's just a geometric ratio. If you get 1, chances are that structure will be cubic. It's not perfect every time, but it's usually got quite good predictive power. If the ratio is greater than 1, you will most likely have a hexagonal or tetragonal structure, and a lot of ferroelectrics fall into this category. If the structure is going the other way, so the tolerance factor is now less than 1, you will get orthorhombic or rhombohedral symmetry, like I just showed 2 slides ago. And if you make the tolerance factor even smaller, you'll probably get to trigonal. And if the ratios of the A and B cations are just too big or too small away from 1, then you probably will not be able to stabilize the structure at all. It will just simply not exist as a perovskite, whatever material you're trying to calculate. So another example, it's the same as before. Calcium titanate is orthorhombic, strontium titanate is cubic. So calcium titanate would find itself here. And if you want to make the structure more cubic, you see here, you substitute calcium for strontium. Strontium is larger than calcium. So you have an increase of the Ra. So overall T increases and you move into the cubic phase. So it's very well explaining at least these 2 compounds and many others. Okay, now we go on to specifically transition metal oxide perovskites. So that means just that the B site cation, the one that sits right in the middle of this oxygen octahedron, is going to come from the D block of the periodic table. In other words, the transition metals. So what's special about the D block? when you put transition metals, well, when you take a transition metal in the vacuum of space, all of its electronic orbitals are going to be symmetric. They're going to be spherical, and you won't be able to see the difference between them. But of course, when you put that ion inside a crystal, so in this case, just thinking about the oxygen octahedron, of course, the orbitals have to somehow break their symmetry. And this is explaining how the symmetry is broken of the transition metal d orbitals inside the perovskite cage of oxygen. So what you get is a splitting between the orbitals which are pointing towards oxygens and the orbitals which are pointing away from the oxygens. You can understand why the T2G, as it's called, manifold, is at lower energy, because the electronic orbitals are negative and the oxygen anion is negative. So this is a lower energy configuration than this one. And this splitting between them in energy is denoted 10dq, which is also called the crystal field splitting. And it's really coming because of this, this difference in symmetry. What you end up with are orbitals that are highly directional. So this means they are very much pointing towards one place in space. And they are very spatially confined. So they're relatively narrow. They're not particularly diffuse orbitals. So what you have is that the electrons don't have so much choice over where they can exist. So there are high electronic correlations. There's a high chance of one electron interacting with another. And you have a strong sensitivity to the lattice. You can imagine if you just shift one of these oxygens a little bit, the energy of these orbitals is going to change a lot. So they will reconfigure very easily. Then one other thing that is important in transition metal oxides is if you take into account the oxygen p orbitals, which are right next door to the transition metal d orbitals, they are also very similar in energy in a lot of compounds. So it means that you can have special physics where there's interaction between the transition metal d and the oxygen p orbitals, and you get hybridization type physics. So what's important here is, of course, how well aligned the oxygen p orbitals and the nickel, what we will talk about later, or the B site orbitals, how well they are aligned in space. So you can characterize this with just the bond angle. So here we call it the BOB bond angle, from the B site cation to the oxygen to the next B site cation, and you have an angle which, in the perfect cubic perovskite, like strontium titanate, it would be 180 degrees. And then for almost all other perovskites, it is less than this. So that's the transition metals and why they are special when they are oxidized. What you have in the end is really rich physics. So what you will see in a lot of review articles is this kind of picture, where it shows you that the different energy scales are very similar for the different degrees of freedom. So if you take into account lattice effects, spin effects, orbital effects, charge effects, they are similar in energy. So they can couple together, they can compete. And what you have is something very highly correlated. So often you will have interactions between these degrees of freedom that you maybe didn't expect. And what can come out is some very interesting phenomena. The other thing, of course, is that it makes it very easy to change phase. So you get very rich phase diagrams. Here is a phase diagram for some cuprate superconductors. So you see you have everything from antiferromagnetism to metal to superconductivity, all within the same phase diagram, all existing very close in doping here. So what you have is super rich physics, and this is the main reason why these compounds are studied so much. Okay, so now I have given an introduction to perovskite structures and the chemistry of transition metal oxides. Now we will talk about nickelates, which takes both of these and combines them. So nickelates, now of course we're just talking about transition metal nickel, which occupies the B site. When you make the rare earth nickelates, it means you are taking for the A site a rare earth, which we will denote R. So the rare earths are coming from the lanthanoid series, and almost all of them can be substituted into this structure. And what you have is a 3+ rare earth ion and a 3+ nickel ion, which is actually rather unfavorable for this nickel. So sometimes it's quite difficult to grow these materials. But what you see is that along the lanthanoid series, because the atoms are getting heavier because you're adding more electrons, protons, neutrons, but also the ionic radius is decreasing. So they get heavier, but they get smaller. And this is because the Coulomb interaction between the nucleus and the electron cloud is getting stronger. So you have the ionic radius, which changes along the series. And as I showed before, for the Goldschmidt tolerance factor, this is very important and determines the structure of the material. It changes the bond angle and thus the physics. So unsurprisingly, you can make a phase diagram where you have the different A-site cations. Equivalently, you can plot the nickel-oxygen-nickel bond angle. So here you have the largest cation going smaller, and the bond angle is the largest here going smaller. So you go from quite a cubic almost structure to a very distorted structure. And then if you change temperature, you get all these rich phases. So at high temperature and for just lanthanum nickelate, you have a metallic state. And as you cool down, you go into this insulating state. Almost all of the compounds do this. And finally, at lower temperature, you enter this antiferromagnetic state. So I'm going to go into a little bit more detail now on these transitions. But first, let's introduce the electronic structure of nickelates. So as I mentioned, nickel 3+ is quite unfavorable. It exists, but not in very many cases. And it turns out that nominally, of course, the nickelate should be nickel 3+, but in fact, it seems that they use this proximity to oxygen in order to stabilize the nickel orbitals a bit better. And they suck one electron out of the oxygen. So you will often see the electronic structure described more like this, D8L, where L represents a hole in the oxygen. And probably what you have in the end for the nickelates is that you have a little bit of D7 character and a little bit of D8L character. It's not a 100% charge transfer from the oxygen, but you have a mixture. And it's weighted by some factors, alpha, beta, that will probably change as you change the nickel, as you change the rare earth nickelate. Okay, so let's talk about the metal insulator transition. This is probably the most famous aspect of the rare earth nickelates. So at high temperature, and this is just going back to the low energy picture where I forget now about the oxygen ligand, you will have one electron in the EG orbital for every nickel. And that's important. It means that every nickel is identical in this state. All the oxygen octahedra are the same size in this state, so we say that it is bond proportionate, and it is charge proportionate as well. This is the metallic state. Then, when you lower the temperature, you go through this metal insulator transition, and you get to the insulating state, which is a bit more interesting. So now you have alternating small and large octahedra, and going along with this, you have alternating empty EG orbitals, and now an EG orbital that has 2 electrons in a high spin configuration. So this is called bond disproportionate, because now there's 2 different sizes of nickel-oxygen bonds, depending on the octahedron you're in, and it's charge disproportionate. And you can describe this, like the low energy picture, which I have sketched here, or in the ligand hole picture, which is much more difficult to sketch. And in both cases, you have a charge disproportionation, either directly on the nickel or taking into account the nickel-oxygen complex. This is why I say charge density disproportionation, because it might be slightly more correct. So what you end up with is this insulating state that is highly disproportionate and has inequivalent nickels. Now, this transition has been studied a great deal. This is just a small selection of the theoretical papers and computational works that have addressed this transition. Just to show you some experimental data now of what the transition really looks like. You have, here I'm just plotting 3 different nickelates, and they are lanthanum nickelate, which is the one with the largest cation. It has the straightest nickel-oxygen-nickel bond. And corresponding to this, it turns out that it's metallic. So that's why you don't see a transition along this line. Next up here is neodymium nickelate, which is a bit more distorted. So this one does become insulating. And you see this beautiful transition from a metallic behavior to an insulating behavior at a certain temperature with a nice hysteresis loop. This is a very clear first order transition. And finally, I'm going to show samarium nickelate, which is here at much higher temperature. And here, okay, it's not as clear, but you do have a metallic behavior at high temperature. This is a log plot, so it's not super clear, but that is metallic. And then you have insulating behavior at low temperature. No hysteresis is observed when you measure the metal insulator transition of samarium nickelate. This could be because it's just happening at too high a temperature for the hysteresis loop to be observable. But in principle, there's no reason why it should not be there. Just to note that these are thin films, these plots. All that serves to do is slightly change the transition temperature. So if you're wondering why the points here do not match in temperature with the transitions you see here, that's why. In summary, you have a strong coupling of lattice and charge degrees of freedom in the nickelates, meaning that when you change the A side cation, you change the bond angle, and you change how stable this insulating phase is. Okay, something that is really nice is, at least for neodymium nickelate that has this clear hysteresis loop, you can clearly see that it's first order also by looking for phase separation. So here is an example. This is scanning near field optical microscopy, which is just an indirect measure of the conductivity of the material with spatial resolution down to tens of nanometers. So when you start at high temperature, the material is a metal. And as you cool down, you get nucleation of insulating phases until finally, below the transition temperature, everything is insulating. And similarly, when you warm up, you get nucleation of the metallic phase again, until finally at high temperature, everything is metallic. So this is a really beautiful first order transition. Now, one of the other transitions is the magnetic transition in the nickelates. This is corresponding to an unusual antiferromagnetic ordering. Unusual because it's along the 1-1-1 direction, so it means you have to draw the magnetic ordering vector, you have to take the diagonal across the pseudocubic unit cell. And it has a periodicity of 4 nickel planes. So in the end, the antiferromagnetic wave vector is 1/4, 1/4, 1/4. So corresponding to the 2 different types of nickel that you have in the insulating phase, and of course all the antiferromagnetic phases inside the insulating phase. You have here, I show blue and red nickels, which corresponds to the charge disproportionation. And it seems that the antiferromagnetic ordering is well described by a non-collinear spin density wave. So that means that as you go along the magnetic wave vector, the spins are not all parallel to each other. In fact, you have these ones which I have drawn out of plane, and then the next ones are in plane, and then the next ones are out of plane. It's probably a little less simple than this picture, where the spins are not exactly in the plane or out of the plane, but there's a kind of spiral with some angle. But in any case, it's pretty complicated. I will not go into any more detail, actually, on the antiferromagnetism in the nickelates. This could occupy a research seminar all on its own. There's a huge amount of work done on this. Some interesting work that's been done on thin films shows that actually the spin density wave changes its character as you make the films thinner, and so on. It's really a lot of very interesting stuff, and I encourage you to go read about it, but I will not talk about that anymore. The last thing I want to mention is that, of course, there are different symmetries in the nickelates. These are maybe not as well studied as the antiferromagnetic transition and the metal insulator transition, but they are there. So at high temperature and for the highest nickel-oxygen-nickel bond angle, we have the highest symmetry, which is rhombohedral. And then as you decrease the temperature or the nickel-oxygen-nickel bond angle, you go to this orthorhombic phase. And then finally, you will cool down even more and go to the monoclinic phase. This monoclinic phase is the one that corresponds to the bond disproportionation of the insulating phase. So this line here is exactly the same as the phase boundary between the metal and the insulating phases. Okay, so there are some overall trends. Let's just mention them briefly. So we have the different transitions. The metal insulator transition decreases in temperature as you increase the nickel-oxygen-nickel bond angle. And this can be understood pretty simply as the bandwidth getting bigger as you go to the right here. So the insulating state is getting less stable. On the other hand, you've got the antiferromagnetic transition, which is increasing in temperature as the nickel-oxygen-nickel bond angle is increasing. So this is just through the magnetic exchange. And finally, you have here, at this point, that the antiferromagnetic transition starts to decrease again in temperature, and this is simply because the metallic state is probably suppressing the antiferromagnetic state through charge fluctuations. Okay, so that was a really brief introduction to the nickelates. Next stop is heterostructures, and then we can finally get into the real stuff. So what is a heterostructure? So hetero just means things are different, and structure means structure. So a heterostructure is a structure of two different materials. So heteroepitaxy is a particular type of heterostructure where you grow one material on top of another and it mimics the structure of the one below. So here we are growing on a substrate. Unfortunately for us, there exist very many different perovskite oxide substrates. So our perovskite oxide films grow nicely on top of them. So there is slight differences between the unit cells of the substrates we use and the films that we want to grow. And that's what this is supposed to represent. So if the substrate unit cell is slightly smaller than the bulk unit cell of the film you want to grow, then the unit cell of the film will be slightly compressed in the plane and it will expand a bit out of the plane. This is called compressive biaxial strain. And likewise, if the unit cell of the substrate is a bit bigger than the one of the film, then it will be stretched in the plane and compressed a bit out of plane. And this is called tensile strain. So biaxial strain you can calculate just by comparing what the unit cell lattice parameter of the substrate is and comparing it to the bulk lattice parameter of the film you want to grow, and you get epsilon xx, which is the biaxial strain. It's negative if the strain is compressive, and it's positive if it's tensile. And worth mentioning is that biaxial strain is quite a long-range effect. It's usually, depending upon the mismatch between the lattice parameters of the film and the substrate, it's usually over 10 nanometers or more. And I have just one thing to mention here, which is that often you will see in the literature, people refer to heterostructures as something a bit more complex than just a thin film. And this is because people are thinking that heterostructure implies that you need to grow more than one type of material. So you have a bilayer or a trilayer or a superlattice or something. Me personally, I strongly believe that heterostructure should refer to just a thin film. So in this simple picture, because there are so many systems where the substrate is more than just a template, a base for you to grow your film on. It's actually playing a super active role in the physics. So that's my agenda that I wanted to push, so you can take it or leave it. So in particular, epitaxial growth means that if you look at the atoms of the substrate, then the atoms of the film are going to fall exactly in registry with them. This is an image of a real film, one that I grew, and you can see the white dots are the rare earth cations of the perovskite oxide substrate, and similarly in the film, and you'll have to take my word for it, but that's the interface, and you see there's almost no difference between the substrate and the film. This is real heteroepitaxy. It means that for all intents and purposes, the film is like a single crystal. It's just very thin. So how do you grow these things? I will not go into too much detail on this, but there are very many methods for growing. In our lab, we are using a range of physical vapor deposition techniques, which in different senses means that you have the ionic species, which are eventually going to become the film, are transferred to the substrate through some process, and the process depends upon the way in which you are growing. So, for example, there's molecular beam epitaxy, where you have the often the individual elements, and you heat them up until they reach their evaporation temperature, and then they just go out into the chamber. This is an ultra high vacuum chamber, until they find the substrate, which is nearby. Pulsed laser deposition is a bit more high energy. So you have a laser, which is very focused, coming in and hitting a target, which can be a single crystal or a pressed powder, which is stoichiometric usually with the film that you want to grow. And the laser pulse is ablating the ionic species, and they are going to the substrate, which is again close by in this ultra high vacuum chamber. And then the highest energy process is a sputtering process using ions, which bombard a target, which again is a pressed powder ceramic target usually, and the ionic species come out and they find your substrate. So the energy increases along this axis, and I would say that the difficulty decreases along this axis. Molecular beam epitaxy takes really a lot of adjustment to get the fluxes of the ionic species right. Here I am modeling sputtering, which is so easy that even I can do it. So you can imagine. So what I want to mention now is specifically for heteroepitaxial growth of perovskites. So because the perovskite structure, as I showed before, is very flexible and it can take on different types of distortion, what actually happens when you grow this as a thin film is not always super clear. So the naive picture would be that the octahedra just stretch or compress depending on the strain that you apply. But what can also happen is that you induce defects. If the strain is too much, this is very likely to happen actually. And this can be defects in the cations or in the oxygens. And finally, and something I will come back to a little further on, is that you can have octahedral rotations. So instead of the octahedron stretching and compressing to accommodate the strain, it will just turn rigidly. Okay, so what I wanted to show with this is just that sometimes when you go to grow a film, you expect one thing and you get completely different properties, and it's just because of this. Sometimes it's just really hard to predict. I will say though that ab initio calculations are making it much easier to predict what is going to happen, because they can really simulate a unit cell taking into account strain and interfaces and so on. So octahedral rotations compose a very active subfield of thin film perovskite oxides all on their own. So this was one beautiful study, but there are so many others. This is yet another scanning transmission electron microscopy image, where these authors found that if your substrate has a different rotation pattern or different rotation magnitude to your film, then at the interface, you can actually impose a bit of this. So here you have LSMO, which is not very distorted in general, but it's quite distorted at the interface because of the substrate. Then you can do cool things like put a buffer layer of strontium titanate that is this almost perfect cubic perovskite, and then you don't have such an effect. Even just one unit cell of strontium titanate, and you can kill this interface effect. So this is a super interesting field. This is a really great review article here. If you are interested, I would say that this is ahead of its time actually, because they wrote this article before people were really looking at these kind of effects. So what they were saying here is that you have to not only think about epitaxial strain, which we know and we understand, and it goes over very many unit cells in general, but you also have to take into account interfacial coupling, which they show here as being something that is much shorter in range. And of course, given the strong lattice electronic coupling of perovskite oxides, this sort of effect, even if it's just a few unit cells, can be detectable, and it can be super important. So to summarize all of this, here I show the same picture again with the correlated degrees of freedom of transition metal oxides, which are often called TMOs, by the way. And then I've added a circle on the outside. So this now is labeled heterostructuring. So here I have identified just a few of the effects that you can have when you make a heterostructure. The only one that is really guaranteed is chemical discontinuity, because that's somehow the definition of a heterostructure. But through these different heterostructuring effects, you can couple into these degrees of freedom of the transition metal oxide. So for example, if you make a film super, super thin, you will reach a confinement regime, which means that the out of plane orbitals will probably not be favored compared to the in-plane orbitals. And then this can, of course, couple to the other degrees of freedom, and you can get very cool physics out of this. So the other thing that I wanted this figure to show is that we are actually working in a field that is at the intersection of two fields that are already super rich, so heterostructuring and transition metal oxides. Now we're looking at heterostructures of transition metal oxides. So very many things happen. If you want to read more, there are a lot of review articles. These are just some of them, and they go into each one of them with a different focus, different examples, and there are just so many that I couldn't even mention them. Okay, so that finishes the introduction section of this talk. So I hope now that these basic concepts are a little bit clearer and that we can go forward and talk about more specific studies. So let's talk about heterostructures of rare earth nickelates. So we're back again here with the bulk nickelate phase diagram. This is already rich. There are very many phases that you can access. You can change the A site cation and you can get different properties. I mean, it's a very active field in itself, bulk or powder nickelates. But when you make them into heterostructures, there's a lot that can bring. So this is a picture I've taken from this review article where you have shown some examples of what can happen when you make a heterostructure. So of course you can start to build up devices. And when you have a material that has a sharp metal insulator transition, there are many reasons why you would like to make that into a device. You can play with different connectivity at the interface. There were some propositions a while ago that by growing in the 1-1-1 direction, you somehow get graphene-like structure. Quantum confinement, as I mentioned, if you make a film very, very thin, then you can have the orbitals that are in general symmetric or degenerate, that they become non-degenerate just because it's out of plane confined. And you can also, depending upon the material that you want to make a heterostructure with, you can have interfacial charge transfer. So this completely changes the chemistry of the material. Furthermore, of course, applications do require probably thin films in order to make interfaces with electrodes and sensors and so on. So this is just a summary of various applications that you could imagine for the thin films and heterostructures of nickelates. And this is from this review article, which summarizes a lot of the work that has been done in this field. One other pragmatic point is that rare earth nickelates are really hard to synthesize as single crystals. Now people are making a bit of progress. Seems to be okay for the ones that are the least distorted. But for a very long time, it was not possible. So this is why studies of the rare earth nickelates really focused on heterostructures for most of the time. So one of the things that comes out, of course, when you make a heterostructure, which we already touched on a bit earlier, is that you have a renormalization of the bulk properties. So that means you're not really inducing new physics, you're getting the same physics, it's just happening in slightly different conditions. So here, this picture is showing the bulk phase diagram, or part of the bulk phase diagram, expressed as a function of tolerance factor, compared to two thin film systems. So these are thin films of samarium nickelate, and these are thin films of neodymium nickelate. And here you see that as a function of strain, which you choose just by changing the substrate that you grow on, you get something that looks quite a lot like the bulk phase diagram. It's just shifted in temperature. And this makes sense because heterostructuring, as we know, does change the structure. It changes the bond angles and the bond lengths. So overall, the nickel-oxygen overlap will be different, the hybridization will be different, the bandwidth changes, and as a result, you have a strain effect on the electronic properties. So it's not really surprising that the metal insulator transition temperature and here the nail transition temperature are affected by this. But what I wanted to talk about in a bit more detail is something that is perhaps more surprising. So this is a study that we have done recently on superlattices of samarium nickelate and neodymium nickelate, which sit here and here in bulk. So they have different temperatures for their metal insulator transitions. So we make superlattices, just alternating one layer with another layer. And we keep the thickness of the two layers the same, M we call it, and we call the total periodic thickness lambda, or the wavelength lambda, and the total thickness we keep the same. So what comes out is perhaps to begin with not super surprising. So when the layers are very thick, so we have a high lambda, you have two different transitions. So one that looks a bit like samarium nickelate at high temperature, and one that looks a bit like neodymium nickelate at lower temperature. And then as you make the layers a bit thinner, the temperatures of the transitions come closer together, and then finally you just have one transition for thin layers, so low lambda, and there's not even a suggestion anymore of a high temperature transition. This phase diagram summarizes the same data, but with a few more points. So here you see the transitions are these black dots, and they are separated at high lambda, so thick layers, and then they come together in temperature until you just have one transition for low lambda. Now, what is interesting is the lambda at which you see this coming together of the transition. So this is happening at 16 unit cells, or 6 nanometers. And this is something that we wanted to understand. Why is this number what it is? So the first thing to note probably is that these are very clearly defined superlattices. There's no intermixing at the interfaces. This is showing the electron energy loss spectra for neodymium and for samarium. And you see, yeah, you go from one material to the other with no intermixing. Here on the right, we are showing two different structural parameters. The delta Z is somehow a measure of the level of distortion. It's just the cation shifts. And here phi, of course, is the nickel-oxygen-nickel bond angle that we know is super important and determines the metal insulator transition in bulk. But in both cases, we don't see, one parameter that's constant over the whole structure. We are constantly going backwards and forwards between a number that is characterizing the neodymium nickelate and a number that characterizes the samarium nickelate. Similarly for the bond angle. So the kind of octahedral rotation coupling and bond angle coupling that has been so widely studied in so many heterostructure systems cannot explain the high coupling length that we have here, up to 16 unit cells. So what we say, if I go back to this picture from this nice review, is that the interfacial coupling here is so small that it really can't explain what we see. Instead, what it turns out to be is that there is a cost of having an interface here between the two materials at certain temperatures. So at intermediate temperature, samarium nickelate wants to be insulating already, but neodymium wants to be metallic. So you would have this kind of mismatch, and then it's not clear what the system would do. And then it turns out, and we used a Landau model to find this, it turns out that there is actually a very high energy cost of having an interface between these two materials at a given temperature, because that represents a phase boundary between this very disproportionate insulating state and this very proportionate metallic state. And this is what is setting the long length scale coupling of the system. So I just wanted to show this example to say that we found something that goes beyond interfacial coupling. It cannot be explained by epitaxial strain because the whole structure is strained. And what we've shown is that there is in fact something else. There's something that is not a physical structural coupling at interfaces that is dominating, and it is determining the physics. So this is something that we're definitely going to pursue in the future. The paper will be out soon, so look out for that. So that was my brief introduction to heterostructuring effect on the rare earth nickelates, with a particular example of what can happen beyond interfacial structural coupling. Now, the last part of the talk I'm going to dedicate to the search for superconducting nickelates. So since basically the high temperature superconducting cuprates were discovered, people have been trying to find superconductivity in nickelates. And I'm going to explain 3 different approaches. The last one, okay, it's a bit of a spoiler, the last one works and the other 2 do not. But it's very interesting to follow the story and see why they do not work. So why did we want to look at nickelates in the first place? So cuprates are very famous high temperature superconductors. Still not room temperature superconductors, so we need to make some more superconducting materials to try to find that. And a lot of people thought that maybe nickel, because it's right here next to copper, could be the way to go. And then in particular, when you look at the high temperature superconducting cuprates, they are copper 2+ ions in the parent compound. And then if you look at the rare earth perovskite nickelates, they are nickel 3+ nominally. So they actually look very similar in that they are both spin half and they both have EG character. So this was not a bad place to start from. And this was what motivated really a lot of study, and still today actually motivates a lot of study on the nickelates. Okay, but there are still some differences between these 2 electronic structures, and that was what was the motivation for this paper, which suggested growing nickelates as a heterostructure in order to really try to mimic the structure of the cuprates. So the idea was something like this, and this might be superconducting. So what is lanthanum nickelate? That was what they were suggesting. Lanthanum nickelate is here on the phase diagram of the nickelates. It is the only one that is metallic and paramagnetic in bulk at all temperatures, so it might seem super boring. Of course, it has some use because it is still a metallic perovskite oxide, so you can integrate it as an electrode in all oxide devices and so on. So it does have application potential. But this particular suggestion was a bit more fundamental. So it was to say, okay, let's take very, very thin films of lanthanum nickelate and we alternate them with something like lanthanum aluminate. And they choose lanthanum aluminate because aluminium is not a transition metal. So basically there is a strong suppression of out of plane hopping of the electrons in this direction. You can imagine these gray layers as just being inert spacer layers essentially. So when you do this, you try to get single unit cells, you alternate it with spacer layers. The idea is that we could end up with an electronic structure that looks like the one of copper 2+ in the high temperature superconducting cuprates. Why is this? So the idea was that you would choose a substrate that applies a tensile strain. And then you would have, in the naive picture, the octahedron of oxygen that is now compressed out of plane and is stretched in plane like this. And this, combined with the orbital confinement that you expect from this kind of thin layer embedded in a superlattice structure with something inert, is that you could end up splitting in energy these orbitals that are in the EG manifold, so the out of plane orbital and the in plane orbital. So you would expect the in plane orbitals to now be at lower energy because they have more space between them and the oxygens. And similarly, the out of plane orbitals should go to higher energy. If you split this enough, then hopefully what you would have is that your 1 EG electron should just stay in one band. You will have then one band at the Fermi level. And this looks a lot like cuprates. Of course, you have to split this a great deal because this electron might not want to be here. It might still want to go here. And also the bands themselves are not infinitesimally thin, they have a finite thickness. So you need to do a lot of splitting. So this is called orbital polarization, meaning that you have one orbital that is fully occupied and one that is not occupied at all. So what we would like is to have 100% orbital polarization to get a single band material. Now, what I have to tell you is that no superconductivity was ever observed for these types of structures. And the reasons are probably numerous. I'm going to explain 4 possible reasons. The first one, I mentioned at the start, that nickelate are actually not so much D7. This was not really appreciated when people started to look at them for superconducting properties in the 90s, but they are more like D8L with this ligand hole. So already you're starting from an electronic structure that is not so good. The Jahn-Teller-like distortion, this compression of the octahedron, might be precluded. So a pure Jahn-Teller distortion would be like this, where you just have changes of the bond lengths. But instead what we have is more like this one. So you might have, instead of changes of bond length, just rotations of the oxygen octahedron. Also, 1 unit cell of lanthanum nickelate is insulating. It's not metallic, which is what was assumed when this type of structure was proposed. And there might be something inherent in the physics of nickelates that wants to prevent orbital polarization. So I'm going to just go into a bit more detail on this point, and this point. So the last 3 points. So rotations dominate. So this is a really nice study that was done with lanthanum nickelate thin films on 2 different substrates, one that gives a tensile strain and one that gives a compressive strain. Lanthanum nickelate in bulk has a Glaser notation that is A-, A-, A-. So it has out of phase rotations around all 3 axes of the same magnitude. When you make it into a thin film, because of the biaxial strain, you're breaking asymmetry between the in-plane and the out-of-plane direction. So unsurprisingly, what you end up with is A-, A-, C-. So now this rotation has a different magnitude to the other 2. In particular, on tensile strain, C becomes smaller than A. So it means that you have almost suppressed the rotation around the C-axis by the tensile strain, and you actually increase the rotations around. So true for a compressive strain, C is now bigger than A, gamma is bigger than alpha and beta, in other words. So you have now quite a high rotation around the C-axis and almost no rotation around the alpha, around the A and B axis. So this is just to accommodate the biaxial strain. It's not too surprising if you think about how the octahedron can rotate to change its overall volume in space. I just want to mention very briefly how they achieved this result. So they use the fact that when the perovskite structure is distorted, you have a doubling of the real space unit cells. So now you have to take into account double the number of atoms in one direction to have a periodic repetition. When you double something in real space, you have it in reciprocal space. So how do we access reciprocal space? With X-ray diffraction. So you send X-rays in, you measure the diffraction pattern that comes out, and now because you have halved the periodicity in reciprocal space, you have extra peaks at half integers. So this is an example from one of my films. So here you have 1/2, 5/2, 7/2 peak, which in a perfect cubic perovskite would not be allowed, but because these things are distorted like so, you get an intensity. You also get one from the substrate in this case because it has the same rotations. Then when you extract the integrated intensity of the signal and you compare it to a simulation, what you can get back again is the magnitudes of the octahedral rotation. So that is what they did in their study, and that is what they showed. And basically the result is that if the rotations are dominating, so the octahedron is rotating much more than it's changing its bond lengths to accommodate the strain, then what is most likely happening is that the nickel that sits inside this octahedron doesn't really feel any change at all. The local coordination with the oxygen is basically not changed. And this is what you need to change in order to have this orbital polarization. So rotations are probably detrimental to the goal of orbital polarization. Now, the next thing that I mentioned was that ultra-thin lanthanum nickelate is insulating. So this is something that has been studied quite a bit already. There is a metal insulator transition if you make lanthanum nickelate very thin, and you see under 4 unit cells, you have insulating behavior. This is for 2 different substrates. The exact threshold under which you have insulating behavior depends a bit on the substrate. But still, it doesn't matter. Everything will become insulating if you make it thin enough. This is something that is kind of general to perovskite oxides with maybe a few exceptions. And so it's something that could be a big problem if what you were assuming when you started out was that you had a metallic material and you were making that ultra thin. Why does it become ultra thin? So one of the things, why does it become insulating when it is ultra thin, I should say? Well, one reason could be due to surface distortions. So this was a really beautiful study by the speaker of yesterday, actually, where they saw that on the surface of the lanthanum nickelate film, you have this buckling of the nickel-oxygen nickel bond angle, and the nickel is lifted out of plane a bit and the oxygens are coming down a bit. So there's a huge distortion at the surface. They were managing to alleviate this distortion a little bit by putting a lanthanum aluminate cap on the top. So this kind of fixes the problem a little bit. But still, if you keep this lanthanum aluminate cap, it doesn't really matter because the sample is still going to be insulating if you make it thin enough. So here is, again, my data. So if you go from a 4 unit cell sample without a cap to with a cap, of course, you have a decreased resistivity. It's much better because the nickel-oxygen nickel bond is not so bent. 3 unit cells, you have an even bigger effect. 2 unit cells, an even bigger effect than that. But still, you start to see at 2 unit cells that this is becoming insulating at low temperature, even if it's in a sandwich of lanthanum aluminate. So this is not the full story. This explains a bit, but not everything. And maybe, as some people suggest, there could be other mechanisms in the end for like 1 unit cell of lanthanum nickelate, such as oxygen vacancies that are making it insulating. Then the last thing that I mentioned, which might be preventing us from reaching superconductivity in lanthanum nickelate based heterostructures, is that they might be orbitally unpolarizable. So a lot of work went into trying to achieve orbital polarization, including really innovative new synchrotron techniques that are described here, and a lot of simulations and computational works that try to propose structures that might give an even better orbital polarization than the one that was originally suggested. But still, I believe the highest orbital polarization that was ever achieved, which was achieved in a tri-layer structure. So now they've inserted a layer of titanate as well as the nickelate and the aluminate. The highest was 50%, which is good, and it's really a super impressive study, really strongly guided by theory, but it's not enough. It's not 100%. So these structures are all insulating in the end. So why no superconductivity? Well, the starting configuration of the electronic state is probably not the good one. We have rotations that are coming in instead of Jahn-Teller-like distortions. So the local nickel environment is not really affected by heterostructuring the way that this proposition was assuming it would be. 1 unit cell of lanthanum nickelate is insulating, so these structures in the end are also insulating. And of course, the inherent physics might just be preventing orbital polarization from fully happening. And this could be just because nickel really does not want to be orbitally polarized. It would rather be in a high spin configuration with an extra electron in the outer plane orbital than to be low spin with 2 electrons in the in plane orbital. So no superconductivity like that. Next story is a little shorter. And I have to start by taking a bit of an excursion to explain what valence skipping elements are. So there are three elements, thallium, lead, and bismuth, which are post-transition metals, which are called valence skipping. And this means that they have one valence state. So this is thallium 2 plus, lead 3 plus, bismuth 4 plus, that is just not observed in practice. It's just not allowed, and you can see why, because it would correspond to a half-filled 6s shell. This is super energetically unfavorable. So what the system does, it will happily be in this valence state or in this valence state. If you want to make a material where you would force the valence state to nominally be one of these ones, what you will have is charge disproportionation between this state and this state. So 50% will be like this, and the other 50% will be like this. It really does this in order to avoid that. And this explains barium bismuthate, which given that barium should be 2 plus cation, forces bismuth to nominally be 4 plus. So you see that would correspond to this type of configuration, not allowed. So that explains why you don't get barium bismuthate to be a magnetic insulator, a magnetic metal, which you would expect since it's a half-filled spin-half material, nominally. Instead, it is non-magnetic and it is an insulator. And this is because it is charge disproportionated. So you have intercalated sublattices of bismuth 3 plus and bismuth 5 plus. Interestingly, you can dope barium bismuthate and then it becomes a superconductor. And this type of superconductivity is often referred to as negative U superconductivity. So what do I mean by negative U? Well, barium bismuthate is a negative U insulator, meaning that it's really the opposite to a Mott insulator, which has a positive U, U being the on-site Coulomb repulsion. Where here you have an attraction between electrons, where they want to be together on one site, alternated with sites that have no electrons. So this is the charge disproportionation picture, which is called negative U. So yeah, when you dope barium bismuthate, as well as some other negative U insulators, you quite easily find superconductivity. And the superconductivity is reasonably high temperature. Here is the famous PKBO superconductor. And the proposed mechanism underlying the superconductivity is that there is a real space pairing interaction between the two electrons that are sitting together, which is mediating superconductivity like a kind of Cooper pair. But crucially, they think that you have to have fluctuations. So you can't just have a complete pairing of electrons, because this would be probably an insulator. So why is this relevant for nickelates? Well, here is the sketch of the nickelate insulating state again. Remember, it is disproportionated. At least you can see clearly here that it is bond disproportionated, but it is also charge disproportionated. So the thought was that maybe the charge disproportionation here is similar to the charge disproportionation that you get in these negative U insulators. But probably what is important is, again, that you have fluctuations. We know that nickelates are like this, just insulating, and people have tried to dope nickelates, but they're not getting superconductivity. So there's something else. So what we proposed was that you should probably try to make a mixture of two different nickelates. So what we did was solid solution of neodymium and lanthanum nickelate being metallic, neodymium nickelate being insulating. And like that, you should have a propensity to disproportionate, but you should have enough itinerancy of the electrons to stay conducting. So the idea to get this was that you should maybe try to find a metal insulator transition that is occurring at around 0 Kelvin. So we tried. What we find is that as you change the content, so between neodymium nickelate and lanthanum nickelate, you have a metal insulator transition. You have a metal at the other side, but then in between you have a gradual change of the metal insulator transition. But you see, you never see a metal insulator transition close to 0 K. So that didn't exactly work out. Either we have something completely metallic, or we have something insulating that's at quite a high temperature, like 80 Kelvin. So we didn't manage to find an incipient metal insulator transition. This does not mean that this kind of approach would not work. In principle, once you find this incipient metal insulator transition, you should just dope it, and maybe that will be superconducting. We just couldn't in this case, for reasons that we are still trying to understand. Okay, last thing, the first success, the first superconducting nickelate. Okay, all I have talked about so far is perovskite nickelates. It turns out that the trick was to not look at perovskite nickelates. So what happens is that the infinite layer phase of the rare earth nickelates has recently been discovered to be superconducting. So here is just a sketch of how they achieve this infinite layer phase. Happily for us that work with perovskite nickelates, we are still relevant in this study because they start from the perovskite phase as a thin film, and then they do topotactic reduction. So it's something that you use a powder which sucks out the oxygens that are sitting on the apical sites, preferentially, leaving behind the infinite layer phase. So when you really optimize this kind of reduction process, what you end up with is some beautiful crystal like this, and then you dope it, and then it becomes superconducting. So here is the summary of the transport properties of perovskite neodymium nickelate. Here it is, it has its metal insulator transition as it should. When you dope the perovskite phase, it's a metal. This is doped with strontium. Then the infinite layer, neodymium nickel O2, is sort of conducting, but it has an upturn at around 50 Kelvin. Then finally, when you dope neodymium nickel O2 with 20% of strontium, that is when you get the superconducting transition, and this is happening at around 10 Kelvin. So this is a super recent result. Already, I'm pretty sure that more than half of the people who were working on perovskite nickelates before are trying to reproduce this. So this is certainly ongoing, and you should look out for all the papers that are coming out now, either trying to reproduce it or trying to understand how the superconducting mechanism works, and trying to compare nickelates to cuprates in the end, because this is what motivated the study of nickelates in the first place. But it seems that the superconducting state of the infinite layer nickelates is not very similar to the superconducting state of the cuprates. So to summarize, trying to make perovskite nickelates look like cuprates electronically did not work. Trying to make perovskite nickelates look like a negative U superconductor like BKBO also did not work. But it seems the trick is to go to infinite layer nickelates, and then you get superconductivity. So this is what we talked about. It seems a long time ago now, but we started with perovskites. I introduced you the structure and explained a few different ways that you can describe the structure, so hopefully it's a bit clearer in future. Then we introduced transition metal oxides and their special chemistry that makes them so interesting to study. Then at the intersection of these fields are the rare earth nickelates, which are perovskite transition metal oxides. Then I showed you some concept of heterostructures like biaxial strain and interfacial coupling. And finally, rare earth nickelate heterostructures that are at the intersection of these three different fields. Then we went on to talk about the search for superconducting nickelates. So trying to make them look like cuprates, trying to make them look like negative U superconductors, and finally forgetting about perovskite nickelates and turning them into infinite layers. But the good news is that we still have to start with thin film perovskites. So all of the work that we have done and all the other groups in the world studying this have done on these materials really makes a very strong foundation to go forward and continue looking for new superconductors and maybe other exciting phenomena as well. So on that note, I would like to thank you for your attention. It's a pity that we could not meet in person, but I hope that you have at least enjoyed this talk. Thank you.
Thank you very much. Thank you very much, Jennifer, for this beautiful presentation. It's very precisely 11:15. I think you're turning really Swiss. Very high precision. So thank you very much. We got a couple of questions. I encourage all of you to ask questions if you want. So maybe we'll start with Galtuvia, who had two questions, and maybe you can just open your mic and ask the questions directly to Jennifer. Gal.
Hi, can you hear me?
Yes.
Hi. So my first question was about this lanthanum nickel oxide, where you said that it's paramagnetic and all the way to zero. So what prevents the ferromagnetic transition or some other magnetic phase?
You mean do you mean ferromagnetic, or do you mean anti-ferromagnetic like the other nickelates?
Any magnetic order.
Anti-ferromagnetic, I guess.
Well, okay, so the other nickelates only become anti-ferromagnetic when they are already insulating. It's probably not possible for lanthanum nickelate because it never becomes insulating. There have been relatively recent studies where they synthesized single crystals of lanthanum nickelate where they find, or they claim to find, some kind of magnetic tendency, let's say. Mm-hmm. It seems now that that is mostly coming from a slight oxygen non-stoichiometry. So even in very pure crystals of lanthanum nickelate, I think that you still don't find any magnetic order. Certainly not magnetic order, and probably not any magnetic fluctuations either.
Okay. My second question was about the negative U insulators. When you said that they become superconductors, you said that the electrons interact in like a Cooper pair way. Can you explain what the difference is?
Yeah, so the theory of negative U superconductivity is not, there's not that many people that have worked on it actually. It's not super robust, I would say. From what I understand, it's more of a, I don't want to say hand wavy, but it's a bit more conceptual maybe. The idea is like a Cooper pair is a pairing interaction, but in momentum space. I said that these pairs of electrons are like a Cooper pair because they're not really a Cooper pair. They are paired in real space. And this pairing is also there above the transition temperature when in the normal state. So they're not really like Cooper pairs at all. It's just that they're suggested to be enough like them that that mediates the superconductivity.
Is there any major difference in the macroscopic superconductivity? Like maybe in the gap, how different does it look from your standard Cooper pair superconductor?
Oh, this I am not sure. Yeah, this I'm not sure.
Okay, well, thank you for the great lecture. I really enjoyed it.
Thank you.
Thank you very much. We have time for other questions. Maybe in the meantime, Jennifer, you said something at the end. You said that superconductivity in these infinite layer nickelates seems to be different from the cuprates.
Yeah.
Can you just say a little more about why you're...
Yeah, so in the first paper where they reported the superconductivity, they already noted this. So, for example, the parent compound of the cuprates, when you don't dope them, so they're not superconductors, I mean, the parent compound, it tends to be antiferromagnetic, an antiferromagnetic insulator. But the parent compound of the infinite layer nickelates, meaning the neodymium nickel O2, so without any strontium doping, it's not magnetic according to neutron diffraction measurements, and it's not really insulating, although it has this upturn. I can show you the data. I think I can show you the data again. It has this upturn. So already they were thinking that it's not really that similar. There's also a large difference in the energy alignment between the neodymium, between the nickel and the oxygen in the infinite layer nickelates, whereas in the cuprates they're much closer together, the copper and the oxygen. So there are several differences. There's a lot of theory papers already. And the paper here is not even a year old, but if you check on the archive, I'm sure there are like 50 papers at least trying to address the superconducting state of these guys. So it's definitely, yeah, like I say, ongoing work. So there's a lot of mysteries here, and people are really trying now to understand it. Hopefully in a few years, we'll have a clearer idea of what's going on.
Thank you, Jennifer. Do you have other questions or comments you would like to address directly to Jennifer? If it is the case, you can just ask your question directly. I do not see all of you, so okay.
That's okay. It means I get an earlier coffee, so.
Mark, do you want to comment or to ask a question?
I would love to, but I have to confess that I went running. I just got back, so I'm sorry. I mean, okay, so
I think you've seen all this stuff before.
Believe me, I would have.
Okay. Jennifer, maybe just one more thing, and so everyone can. Okay, I see that Ricardo has raised his hand. Ricardo, you want to ask a question? Go ahead.
Yes. Thank you, Jomar. I have one question. I mean, a lot of the cuprates, they started from perovskites and went to double perovskites, right? To get the high TCs. Was there any attempt on that on the nickelates or the bismuthates, for instance?
To get double perovskites?
Yeah, and get superconductivity. Like lanthanum strontium cuprate, it started from a perovskite attempt, and then they doubled the cell and went to the double perovskites, and that's where high TC appeared, right?
Yeah.
So, were there any attempts on the nickelates or any ideas on that area?
The only studies that I know on the double perovskite nickelates are more geared towards trying to make multiferroics. Actually, I'm not really sure why they didn't try this for superconductivity in particular.
Okay, well, thank you.
Okay, thank you. Jennifer, I was thinking, you also mentioned this negative U physics, which is very appealing. Also, as you said, it's not as developed as say, conventional superconductivity. For LNNO, do you want to say a little more or to explain why? Okay, well, I'm not sure we know, but to explain why we cannot reach the point we wanted to reach?
Oh, yeah, well, okay, then to go back. Where did I go? I went too far back. Here. Yeah, so you mean why we don't get metal insulator transition close to zero?
Yeah.
I mean, already we're not sure if we even got that. Would that be superconducting? Okay, after doping, it's not clear. But why we don't manage to get a metal insulator transition close to zero? Yeah, this is something that is we're trying to figure out. So the first thing that we thought was the symmetry might be important. So neodymium nickelate has orthorhombic symmetry, and lanthanum nickelate has a rhombic heterosymmetry. So at some point during this solid solution phase diagram, you should go from one symmetry to the other, and maybe this is suppressing a metal insulator transition that would otherwise have been much lower in temperature. That was one thought. It doesn't really seem to be the case. Now we are thinking about more spin fluctuations in the insulating state, and how that might change the entropy and eventually destabilize the insulating state even when the metal insulator transition is quite high. So you don't get, you don't reduce it anymore, you just go straight to the metallic state. There are a few different possibilities.
Okay.
Yeah.
Okay, thank you. I see that we have another question from Zitao, who is making an analogy between the lanthanum titanate and the nickelate. So you can ask your question to Jennifer.
Hello?
Yeah.
Hi. Very nice presentation. I wonder as probably you know that the titanium 3+ only have one 3D electron in orbit, and unpaired nickelates also only have one unpaired electron in the EG orbit. Do you think there's any similar magnet or the transport behavior can be found in the 3+ titanium?
Yeah. Yeah, I see why you ask. So lanthanum titanate is a Mott insulator, I'm sure you know. Whereas the nickelates are called negative charge transfer insulators. So if you look at the periodic table, in fact, I can probably just show my slide with the transition metals. Here, titanium is really far on the left of the periodic table, whereas nickel is really far on the right. So actually they have quite different behaviors, even though this has one 3D electron and this has one EG electron. So it's actually not super similar because this guy is T2G, so its orbitals are completely different from nickel, which is EG. And if you, I don't remember where I have this picture either, but I don't know, the next slide. If you look here, you see that the T2G orbitals actually don't line up with the oxygen 2p, whereas the EG orbitals do. So one thing that comes out of this is that, and this is general to the right side of the transition metal block, is that here in the nickelates you have quite easily hybridization and charge transfer between the nickel and the oxygen, whereas in the titanates, and lanthanum titanate is not an exception, you have not so much interaction between the titanium and the oxygen. And for the nickelates, this hybridization, this nickel-oxygen hybridization is super important for the physics. So you can't really compare it to the titanates in the same way. Does that answer your question?
Yes, that's perfect clear. Thank you.
Okay, thank you.
Thank you very much. I'm looking, I do not see any other question. So your very last chance to ask a question to Jennifer. But I think everyone seems to be happy and with the talk. Okay, so I think we will stop here. Jennifer, thank you again for this beautiful presentation. I'm clapping for everyone. And so we stop here, and I look forward to seeing you all later this afternoon or next week. Okay, bye-bye.
Bye.
Bye-bye. Bye-bye.